Today's session is on the CASTOR robot, and I would like to introduce the speaker of today's session, which is Carlos Cifuentes from the Colombian School of Engineering, Julio Garavito, and two master students who will be sort of co-hosting or co-presenting, Diego Casas and Juan Maladona, on a talk on a soft social robotic or compliant social robot. We'll start the session with a short video which will be released after the session, and after the video we will go into a question session.
Hello everyone, thank you for this invitation. My name is Carlos Cifuentes. I belong to the Biomedical Engineering program of the Colombian School of Engineering, which is an agreement with the Rosario University. I am also the leader of the Center of Biomechatronics, and today I will talk about CASTOR Robot, an open source social robot for therapy with children with ESD. In this talk, I will introduce the project, the motivation, and with the help of two students, we will talk about the electronic and the mechatronic design of the device, and also how to integrate this in or how to develop this in future works. This is the first part of the seminar. The second seminar will be on the 18th of December, when the Professor Marcela and Maria Jose will explain about all the participatory design involved in this work, and also they will talk about the clinical validations. However, I will show some outcomes in this field in the human studies that we have done during this project. Firstly, I would like to introduce our center. We have many agreements with clinical institutions and rehabilitation centers in Colombia and also in Latin America and around the world. And we work with this methodology. We usually develop qualitative studies in order to identify opportunities by means of observations and questionnaires to understand the needs of the clinicians and also the needs of the patients. With this valuable information, we develop tools that we can divide into possibilities. One of these is the estimation of parameters that can provide information about the performance of the patients during the treatment that will help the clinicians to follow up the patients, and also the robot behavior and the control strategies to integrate robotic systems in these scenarios. We evaluate the effects of this technology on these populations, employing usability tests, short-term use validations, and long-term validations. This is most of the methodology that we implement in our center. We involve engineers from mechanical, electronic, and also biomedical engineering, but also clinicians in the development of these projects. In these videos, you can see some of the studies that we are performing at this time. So we can summarize our works in 3 lines. Firstly, robotics for physical assistance. In that part, we have been working in development of several wearable robots for the treatment of different pathologies like cerebral palsy, stroke, or spinal cord injury. You can see in the videos also exoskeletons for lower limb, ankle joints, and also hand exoskeletons. And we combine these devices with smart walkers. These devices also help patients or users in mobility and in some applications in daily life. In the center part, we can see robotics for cognitive support. These robots help clinicians in the daily work. Firstly, you can see robots for autism, that is the main topic today in this talk. And you can see also robotics that work with clinicians and in several scenarios like neurological rehabilitation, where the social robot are focused in specific variables that are important to follow up the patients. In that case, the robot is helping the clinician measuring the posture of the patient during the treatment and encourage the patient to perform a good posture during the treatment, which is very important in this kind of rehabilitation. After that, you can see robots supporting cardiac rehabilitation, which is also one of the works that we are working with researchers of Plymouth University. In that field, we have been integrated several sensors to monitor the patients during the treatment and encouraging them to develop the long-term treatment of rehabilitation. We have many publications in this part, and hopefully we can disclose this later. In the third part, we can see affordable robotics, when we are developing open source robots in order to be transferred to clinics to develop treatments of studies in clinics and also in universities. And it's affordable tools that is made with 3D printing and open source hardware. You can see the CASTOR robot that we will talk today, but also Deflex, which is an ankle exoskeleton, which is also free access in GitHub. And also you can see a hands prosthetic that we are developing at this time. So this work is impossible to do only with our group. We are collaborating with many groups around the world, some companies and some universities in Latin America, Europe, US and UK, of course, and in Japan. Our collaboration with Plymouth University started in 2016 when we got the first project funded by the Royal Academy of Engineering with the program Industry Academic Partnership Program, Colombia, UK, which is focused in integrate one university in UK, one university in Colombia, and one company. In that case, we collaborate with a company that develop robotic tools or commercialize robotic tools in Latin America, and we developed several studies to understand the possibilities of social robots in some scenarios like neurological rehabilitation, cardiac rehabilitation, and ASD treatment. As you can see, this has been a great part of the work in our group, and this project was called Human Robot Interaction Strategies for Rehabilitation based on socially assisted robotics. You can see in the pictures that we did many visits to Plymouth, and researchers and professors from Plymouth came to Colombia for develop seminars and research. It was a very interesting project that is still giving a lot of outcomes in research with the topic that I told before, which is the cardiac rehabilitation. One of the outcomes of this project was this study that we involved 30 children and 12 therapies, and we analyzed how they developed the treatment, the ESD treatment, and we understand that this is a therapy that is performed almost daily during the week. And what are the interactions between the clinicians and the children? We can see physical interactions to promote good posture, reduce bad habits, provide instructions, train emotions, and also other interactions. And we also asked to the clinicians if they see useful the robots in their work, and we saw that around 70% of the clinicians say that the robots are useful or very useful. The technology, so they will be interesting, so they prefer don't say that it will be useful. So most of the population or clinicians in this field are really interested. So after that, we decided to write this project, CASTOR Project, and we started to study the literature of social assisted robots in autism, and with experience also in the Plymouth University with Professor Tony Alpine. There are evidence that robots assist in the diagnosis process and also improve risk factors like eye contact and joint attention, and also increase self-initiate interactions. And during the simple therapy, robots encourage basic communication, imitation, and emotion recognition. So you can see in the video some examples or successful robots in therapy and also commercializing around the world. And to deploy the robots in Latin American clinics or in general in developing country clinics is complicated because the robots are hard and stiff and unsuitable for physical interaction. So these robots can be harmful for the child or both. And we can see in the video one open source robot, which is Honor robot that we usually use in this research, but we found that it's very fragile, and also we had some problems with now robot. We had some broken robots in the lab, and we have to send them to US to get recover and back to Colombia to continue studies. So it's quite expensive, and the price in Latin America is around £10,000. So it's difficult to manage for any clinic in developing countries. So this is the main problem that we want to fulfill with this research. And we can see here the three objectives of this project. So we started this with the design and the evaluation of a social soft robotic platform, looking also at open source platform. And the second objective is oriented to develop soft actuation system, looking at physical interaction. And the third objective is oriented to develop sensor subsystems to monitor the interaction with the children. So this project is mainly led by Plymouth University and Colombian School of Engineering, but there are also interesting collaborators like Tejido de Sueños, which is a company here in Medellin that they develop participatory design in many devices and tools for children. And they are the company partner in the project, but we also have the collaboration of UFES University, which is a university in Brazil. So, and the clinic is the rehabilitation clinic Howard Gardner, which is a clinic with 2 headquarters in Bogota, which will be mainly the focus of their patients in this project. So here we can see the picture when it was the kickoff of the project, and we were with the partner, Tejido de Sueños, the company, and also the partner from the clinic, and also our collaborators, Tony and Martin Stolling from Plymouth University, and we started the project in that way. We firstly started to explore the use of social robots using Honor robot, developed in Belgium, and we integrate this robot and start to develop sensor system to monitor the interaction between the child and the robot during the treatments. So we started with the joint attention assessment when we located 3 different objects in our room, and the clinician, the psychologist, asked to the child to look at the different objects in the room. And with a multi-camera system that we developed in this project, with the help of a PhD student from Brazil. And we detected the visual focus of attention of the child, and we expected to use this system in that time in the next studies in the world. During the same time, we started to work in the design of the project, in the design of the robot that I will talk later. So this was one of the outcomes of this project when we developed a system to detect the face and the face and the orientation of the child and the visual focus of attention that we present in this article. That this is very interesting because we involve a significant sample of children in this study when there were two groups, one group of children with autism and one group with children with other special needs like Down syndrome. And in that case, we evaluated the same therapy and we found specific behaviors of the child that we can demonstrate with quantitative data obtained from the system. And this is a very good, very interesting outcome for the state of art that it's possible to detect specific behaviors in children with autism. And so with this first evaluation, we demonstrate to the clinicians the, the possibility to collaborate with the robots during the therapy. And it was in part as sensitizations to use the robotics to, in next stage, start to develop the participatory strategy design with them. But after this study, there were many research questions. One of them is the effects that we see according to the children with autism, that they are very interested with the robots and the performance actually increase with the robot in the scenario of the therapy. So we decided to develop a study during 10 sessions when we also were curious about how is relevant the role of the robot and also the clinicians in this therapy. And the robot, we changed the role of the robot. So at the beginning, the clinician had the 100% of the share of the therapy, and in the second therapy, so the robot started to say greetings or say some words. So we started to increase the percentage of the participation of the robot in every sessions. So in the 5 or 6 session, the robot had 50% and clinician 50% of the share of the load of the therapy, and in the end, the robot has the 100% control of the therapy. So here we want to study how is the best combination of the control of the therapy between the clinician and the robot. And we found that the best combination that provide the best performance for children with autism is when there is around 50% of the clinician and 50% of the robot. So this is also in our way of working in our group, that we present the robots like a tool, that the clinicians are really important and the robots won't replace them. So here we can see with quantitative data that also support that the best combination is the robot and the clinician doing the work to increase the performance during the rehabilitation. So this work is now under evaluation, but we expect to discuss more information after being published, and we hope that it will be accepted. So after perform this sensitization part, some intervention with the robots, we developed a participatory design that is published in this article. And it will be presented in the next seminar with Professor Marcela and Maria Jose. They are also part of the project, and they are mostly in charge of the studies with the children and the clinicians. So the interesting part here is that we discover what are the needs and what are what the clinicians and the parents and the child expect of the robot, and we found some cultural aspects that are really interested to involve in the design of the robot. So in the next seminar, you will get more details about this methodology. I just want to summarize all the outcomes of this project. After develop all the participatory design strategy, we find out that there were three designs that children and clinicians and all the populations were interested, which is one design like a robot, one more fantastic, and one like a child. And in this paper, which is also under evaluation, after perform a validation with children, we found that the outfit of the robot is the best option that the children feel more attracted to interact with. But there are many details in this study that you will see in the next seminar. So we were also working while all this part of the design were performed. We worked with the team of the mechatronic team, which is integrated with Diego and Juan, that you will see later on in this talk. And so with them, we developed this robot, the internal part of the robot. So it's possible to change the outfit depending of the population that is intended to use the robot. So we expect also that developing more studies around the world with this open source platform. So in this paper, we release the design, all the development, and also the repository in GitHub to encourage researchers and people interested to integrate these social robots in the research of autism treatment. So you will see more details in the next part of the talk. Also, we did many research. We have many research outcomes, but also was very interesting the interaction between the researchers in UK and Colombia, and also our students. So this was one of the seminars that we did here last year before the pandemic, and was very interested because we present all the results of the project until this time, and also we invited some clinicians to this seminar, and also looking for next collaboration with other institutions. After this year, at the beginning of the year, we finished a study with children when we really wanted to understand if the physical interaction has a really importance in the ESD therapy, because in that time that we already have the robot, and we also involved a significant sample of children in this study when we compared two groups. One group that was invited to interact with the robot during the therapy, and other group that was prohibited the possibility to touch the robot. And we found significant results according to the tactile interaction, and also with the with the possibility to interact with the robot, in that case, this work, we also are very happy because we received this week the news that this work was accepted in HRI conference, which is the best conference in this field. So Professor Marcela and Maria Jose also will give some details, but maybe you have to wait next year in the conference to see all the details of this study. But this is very interesting because we found that human robot interaction really are a interesting tool for clinicians. In that way, it's robots, social robots that provide this capability to be to do this kind of interaction and be easy to repair during the clinical interventions. It has a lot of potentials in long-term study to understand the effects of these robots in this population.
Hello everyone, my name is Diego Casas and I am mechanical engineer and currently I am master student from Colombian School of Engineering and I am in charge to design of the mechanical structure of CASTOR Robot, and we'll go to talk about what is the development of this project.
This is the sizing methodology. Taking the line of sight into account, we can answer a question like how big the robot should be. This through an ergonomic study that includes a measurement of the different children, taking into account the two maximal and minimal height cases. That result is considering two scenarios. The first scenario is when the robot is placed in front of the children at the table. And the second scenario is when the robot is put on the floor to emulate the pair interaction. This study showed that the optimal proportion of the robot gaze is between 38 and 49 centimeters.
Now I will go to talk about the development of the CASTOR robot. This robot has 7 degrees of freedom to generate the movement of the arm and neck. Additionally, this robot has 1 degrees of freedom in the middle of the structure to work as huggable structure. This robot has 3 main modules, which are the arm module, the head module, and the huggable module. Arm and head modules are series elastic actuators system, and the other one is a pneumatic system. Those systems allow that the CASTOR robot has been a novel proposal.
This is the first module and is in charge of actuating the head of the CASTOR robot. The head is one of the most critical parts of the robot because it's big and heavy. There is where the electronic element and electronic system is placed on. On the other hand, it's where the children put the major part of their attention in therapy. This system has one elastic element between the motor and the head, decoupling the motor from the direct load. The elastic element is constructed with 4 aluminum bars, and thanks to the flexion properties of this material, we can generate a part that's able to deform around the motor axis. So when each bar is deflected, our system makes a rotation, absorbing the energy from the physical interaction, as we can see in this video.
The second is the arm module. This module includes 3 degrees of freedom to move the arms This arm has 2 degrees of freedom in the shoulder and 1 in the elbow. This part of the robot also has series elastic actuator, but in this case, the elastic element works a different way. This elastic element is it's coupling as a pulley between the motor and the joint, as we can see in the figure A. This elastic element is constructed with a couple of materials. The first one is an elastic material, and the other one is a rigid filament that is placed around the elastic element. This is with the proposed to have a material with the behavior similar to the human tendons. That is to say that the beginning of the motion, the elastic element works and absorb the energy to protect the motor. But all the middle of the actuation, the rigid element works and allow a good torque transmission. Therefore, it's important to make a preload of the element to improve the actuation, as we can see in the figure B. The last is the huggable module. This module has a couple of pneumatic cylinders with 16 newtons each one, with the purpose of absorb the energy from the impact or hard interaction with users. That idea is extracted by how works the human body in a moment of being hugged. The human body, thanks to the clavity function, can deform the structure to absorb any impact, and this is the same conception of the huggable module, as we can see in the videos. Now I want to talk about the materials and fabrication method. One of the main features of the CASTOR robot is that it's so easy to reproduce. That's to say, the major part of the CASTOR's parts are a CAD that is printable in any 3D printed machine, and the rest of the parts are commercial elements, such as 4 couple of bearings and the motor screw. The CASTOR structure has 30 printable parts, and all of these parts is fabricated in PLA, that it's a resistant and easy to find material. This is the design strategy of the CASTOR robot, and this is based on displacing the mass of the part as far as possible from the neutral fiber. The neutral fiber in a flexion test is less stress, therefore put the mass in this segment is to lose material. The idea is to put the same mass in the disposition where is increased the inertia, as we can see in the figure. You can see the behavior of the two parts with the same mass and the same material, also with the same test slot. With this figure, it's possible to compare and to see that the stress in the prismatic design is so much more than the CASTOR design. That shows that it's more resistant and rigid to manufacture a part with this methodology. This is the mechanical study of the series elastic actuator system that have the CASTOR robot. This test was made with the purpose to evaluate the behavior of the elastic element of each system. The setup is a couple of motors coupling with an obstructed joint. One of the motors has the elastic element between the motor and the joint, and the other one is attached directly to the obstructed joint. The system of the motors is able to give data of the load at each time that show how much effort the motor is making. These are the result of the mechanical study. We can see in black lines the behavior of the motors without the elastic element. On the other hand, in orange, the CASTOR system. This drill is based to actuate the motor, increasing the angle in 10% until arrive at the maximum range of the joint. The first thing that I think that it's important to result in the is the quantity of energy that the CASTOR system is absorbing due to the load in the motors. With the elastic element, it's so much less than the load of the motors directly coupled. On the other hand, we can see that the response that we wait at the moment to design the actuation of this system, it's reflected in this test, where the more load it's to use at the moment to transmit the torque, as above mentioned, with the human tendons. Which is so important in a structure to keep physically interaction with the user without any risk. And this is, I think that it's a good thing to take into account at the moment to design different kind of social robots.
Hello everyone, this is Juan Camilo Maldonado from CASTOR Project. I am electronic engineer from Colombian School of Engineering Julio Garavito, and I'm gonna to talk about from all electronic of CASTOR Robot. Okay, let's start. How to power CASTOR. Basically, CASTOR needs 12 and 5 power supplies, but we designed a distribution board to only use one power supply. This distribution board has a regulator to convert 12 volts to 5 volts, have USB connectors for Raspberry Pis, and terminal blocks for power up the on-hardboard and the dynamic cell motors. Now, the CASTOR platform. CASTOR integrates two Raspberry Pis Model 3B Plus boards to control the hardware, and Raspberry Pi 1 is located at the bottom of the robot and Raspberry Pi 2 on the top of the robot. The Raspberry Pi 1 controls the dynamic cell motors and the on-head board. These dynamic cell motors generate arms and neck movements, and the on-head board is a Raspberry Pi hub, capable to control a speaker, touch sensors, and the servo motors, in this case the phase motors. The Raspberry Pi 2 controls the eyes bonnet board. This eyes bonnet manages 2 LCD screens, the eyes of the robot. With this board we can change the color of iris, the color of eyebrows, the size of the pupil, and direct the gaze. For Raspberry communication, we create a Raspberry Pi network, where Raspberry Pi 1 works as a master and Raspberry Pi 2 works as a slave. And for easy connection to CASTOR, Raspberry Pi 2 generates a Wi-Fi network. For CASTOR operation, we use Telegram. Telegram is an easy tool for generating interfaces. With Telegram, you can control all the robot. Emotions like happiness, sadness, anger or surprise, and movements like read, dance, or pointing someplace. Finally, we can control voice lines and sounds. This is a short video of CASTOR operation.
Hola, me llamo Castor. ¿Cómo te
In
llamas?
this case, we press the greetings button and CASTOR says, hello, I am
Vamos a
CASTOR.
jugar.
And after we press the button let's play and CASTOR says let's play. This interface is fully modifiable and you can change for all you need.
Otra vez. Muy bien.
The CASTOR software is based on Linux distributions and ROS. All the functionalities and communications are accessed through nodes, topics, and services, all available on the CASTOR Robot repository. The ROS architecture is mainly composed by 5 nodes. The Telegram node, where we can create interfaces, the motor behavior node for established movements and dynamic cell motors operation, the facial behavior node to control face motors and generate emotions, the eyes behavior for control the gaze and size pupils, and finally the speaker node to control sounds and voice lines. Okay, finally, this is a ROS diagram. Maybe it's confused. In the diagram, we can see that Telegram node is the main node and communicates with all nodes. With these nodes, CASTOR can dance at the same time that the robot plays a song and is happy, and say try again with a happy face or sad face, and combine movements of emotion with sounds of voice lines.
So this was the presentation. Finally, I would like to invite people interested to the project to visit the articles already published, to read them, and also ask us to any questions that we'll have. We still have some time in the seminar. And also, I want to say that this project is also continue with Plymouth University. Now we are planning a new stage of the project, collaborating with Professor Swen. So we are planning to reproduce this robot now with the information that we have already published in the project, and we have also some funds that we will use now to develop one CASTOR robot that will be available at Plymouth University, and we want to develop studies also in Colombia and UK, and share protocols, and also trying to find more consolidated results involving more institutions in this study. So we will be happy also to integrate more clinicians in this work. And finally, I also would like to invite the attendees to the next seminar that will be the 18th of December, that when Professor Marcela and Maria Jose will explain in detail of the human studies and all the protocol design involved in this project. So thank you very much, and I will be happy to answer any question that you have. Thank you.
Thank you very much for that, for the talk, and for this really great overview over the project. And as Carlos just mentioned, there will be a continuation of the project. So we're currently in the process of investigating the resources for building another one of the CASTOR robot series here in Plymouth. So if you're interested in collaborating, or if you want to spawn off your own version of the CASTOR robot, do get in touch with us. And are there any questions? I will stop my video now, but if there are any questions, feel free to ask. I will stop the share. So the video will go live as well onto our website, so you can watch it later on and can share it. But do get in touch, and I'm now opening sort of the room for questions towards Carlos. So if you type in the question, if you don't want to enable your microphone, that's fine, and I will repeat them so that everybody sort of can join in. Ray has a question.
Can I ask? Hi. Muchas gracias para la presentación. We run a project in Cornwall. Sven is part of it, called EPIC, where we are trying to help small companies get started. Are you interested in getting a sort of an offshoot of your work, starting up with some students or somebody else in Cornwall? We also have great networks of people, clinicians, and also patient groups interested in autism. So we've got a ready-made networks where this could be trialed. So my question is, what's the next stage for you in terms of what do you think needs to be done in terms of getting this to the stage where it can be sort of rolled out in numbers rather than being just a more of a laboratory robotics project, but much more of a healthcare project? Sorry, a bit of a long question. I hope you got it.
I can answer the first one before Diego and Carlos can go into the actual details. So the first part is, as we're building a version of the CASTOR robot now, by the end of the start of next year, we will be able to test and work with clinicians locally on getting insight into what's needed for them from the current version for a final version. And I think after that, because it's an open source project, there is chance of moving it forward to a mass rollout. But that's something which Carlos and Diego have to talk about more in detail. But the first step is we'll be able to have one for testing here soon. So in half a year, that should be ready for having something to test, and then we can move further forward. But Carlos, what's your view?
Yes, thank you, Sam. Thank you, Ray. And yes, we would like to continue with this idea. This was the plan also with Martin, that Martin helped us with the connection with Sven in this continuation of the project. The project supposedly had to finish this year, but with the pandemic, the Royal Academy extended maybe to the next year. We still have some funds that we expect that Sven can use to recruit a student and buy some parts, and we can support them to replicate the robot. And also, it could be a nice experience to report that in the literature. How is the experience to report this, to reproduce this robot? So this is one of the main objectives now. But Sven is also open the view of this project, and he's involving more clinicians and students, and Ray will be happy to collaborate with more people in UK, because as this project is looking at developing countries, but we have seen that the real problem in the research of autism is the long-term evaluations. The researchers don't know if the results are related to that the children are growing, or maybe the tools or the effort of the clinician. So with this kind of tool that we can each repair, and we can release in the clinic, and the children and the clinician can touch in any way, we think we'll have consolidated results involving multi-center evaluation. I think the next part of this research is try to involve more clinics and more countries around this. And I think also more of the researchers in this field, there are many known robots around the world, but most of them are not open source. They are expecting how to integrate more clinicians and developers significant samples of users. And also the reviewers always replied, we need more sample, bigger sample of users. You need to integrate more clinics. But this is difficult, no? And also right now with the pandemic, it's also more difficult. But we have seen also that the clinicians are really interested in the robot, because at this time it's difficult to develop this therapy with humans. So we are thinking in how to deploy the robot controlling the therapy, and maybe the clinician can be like a virtual agent, or can participate by a screen in the room in the therapy to continue this therapy. Because at this time in our country, this therapy with children with ASD is doing by telerehabilitation, with this an issue also. And so there are many things. So continue trying to integrate multi-center research in this topic, involving more researchers, and trying to do a big campaign to integrate more universities to develop, to integrate, improve mechanical, improve electronic. And we have also many ideas to improve the robot in the next version, but maybe Diego can explain us. And also we would like also, if a company is interested, could be also a possibility, but we are still more focused on understand the long-term effects of and the possibility of a multi-center evaluation. I don't know if I'm clear with the response.
Well, am I allowed another question, Sven? I'm sorry to hog all the thing, but so are you presumably can I take you up the other end of the age spectrum for a while, and I'm sure that you must be aware of the work that's been done with older people and dementia with robots there, where there's been this long-standing robot Paro, the seal, but work that our colleague Hannah Bradwell's done in Cornwall has shown that probably a very simple, you might call a smart toy is actually just as good as the rather expensive robot. So I was wondering if what it's going to cost at the moment to try and produce the robot that you're working on at the moment, and then what would be a cheaper alternative, because these things need to be cheap to work in any sort of mass delivery of them.
I can answer some of that. As we could see from Diego's part of the presentation and the one from Juan, most of the design is free. The design is built using rapid prototyping methods, which is good for getting initial prototypes out. But the cost is also of the material not that much. So the most expensive parts currently from looking at the robot as an external who hasn't built one is time. And that's something which can be streamlined. So the materials are not super expensive. The motors are expensive right now, but everything else is centered around being able to rapidly be produced. And as we could see in the current situation with the face shields, 3D printers scale up quite well actually, and Plymouth is not in a bad place for that. So we have a massive pool of 3D printers available. So all the parts can be streamlined and printed quite fast to basically speed up the production of multiple units in the first step. But I think in terms of readiness levels, so if we're looking at technology readiness levels, the CASTOR is not in a commercial sort of ready level yet. So it's not beyond 3 or 4 if you look at the 6 levels of readiness. So it needs, as Carlos said, a bit more testing. So we need a bit more feedback before a company could commercially produce it. But what is still possible already, as it's open source, is approaching this from a company point of view, so they can work with us together to get the product to that stage. And that's one thing which is possible. So sorry for stepping in there, but is there any sort of more feedback from you, Carlos, towards that? But I think it is possible, and it's not there yet, but we're approaching a point in time where we could sort of scale up the production quite a bit. But it's because everything right now is centered very much on research, which is important initially. We're not there yet to say we can take the robot as is and print 10,000 of those. In terms of the costs, the robot is not super pricey right now in terms of production. So it takes a couple of months to build for one technician, and that's building everything from scratch and getting the components in. So that's sort of why it takes half a year to get the next CASTOR built with us, with a technician with 0 prior experience and only being sort of guided by the research Carlos, Juan, and Diego did, and building it with them. But that's a process which automation can speed up quite a bit once we're there with the final version. But maybe Carlos and Martin could say a bit more about that.
Yes, of course. Yeah, I think the price, maybe Juan can clarify that, but it's around 1,000 pounds, 1,500 pounds, maybe less. In producing one, yes, of course, but maybe Martin can clarify this experience to start with an open source, because actually we copy his strategy, how to deliver an open source robot, and how it will be nice how he transferred that to a company. It could be nice to hear the experience of Martin also.
Yeah, sure. Thank you, Carlos, and thank you, Sven, everyone. Yeah, I think I really like this project, of course, but I think you're right. You're in that stage now where you have a really nice open source platform, which is great. People can replicate it. You can do replicable experiments across the world in different groups. Compare what happens in different countries, etc. But I think also Ray's right. This now, if you want to really have an impact, you want to get it produced and get it out to more than just the participants of these research projects. And yeah, I think what we did, I mean, some of the same type of technology we would take in towards agricultural robots in the spin-out company I've helped set up, and it's been we've gone through some of the same steps, and it's certainly possible to I think also to take the CASTOR platform and make it into a product. Sven, you're right. It's that a lot of parts are cheap, and probably the most expensive parts there are the dynamical servos used. You're talking a couple of £100 or something, or a bit less maybe for these ones, but it's that kind of range. And what we found in our project has been that you can easily replace those with less servos with less options in them. These dynamical servos are built for research. And they have a lot of options that you don't normally use, so you can replace them with something cheaper, maybe a quarter of the cost or a third of the cost. So that would bring the price down further. And then to me, it sounds like you're in the stage where you would need something like funding from Innovate UK or equivalent in Colombia or somewhere else to help someone take this and make it into a product, make it into a prototype that can like a commercial prototype that could then help you attract investors, and then it becomes a product. So maybe it's that kind of time that you need an Innovate UK project or similar. But you also need someone that's interested in taking it towards a product. So who will do this? Is it a student? Is it someone related to Sven or to Carlos, or all of you together putting together some kind of consortium to do this? I don't know, but it's a fun position to be in. I think you have a possibility here, I think.
Just to step in there, I think Ray is in an interesting position right now because of Epic. We have something to prepare for through Epic, a company, to step into a range where they can sort of have a first pilot to investigate the technology, and then we can move further towards Innovate UK or towards sort of larger grants, because Epic is sort of an incubator for early ideas in e-health and robotics in the Southwest. So if we get a local company interested in the topic, that's where we're ideally positioned through Ray and Epic to support this and to bring CASTOR into a realm where it could be commercially applicable. So I think this is an interesting conversation we should continue after sort of the talk. Are there any other questions regarding that? So I think Ray and Carlos and Martin and me, we should have a chat at some point later on about a continuation of this and bringing it into Epic too. So are there any other questions? Sort of people want to know anything else about the project?
I have a question actually, Sven, more related to, so across the presentation, so it was not clear to me, I mean, the possible set of interactions with the robot, and which were among all of them the most preferred by the participants. Okay, do you have any study about the types of interactions which basically occurred more often between the participant, the children, and the robot itself? What is your finding there? What did you find that more engaged?
I think some of that will be answered next week on the 18th.
Okay.
But maybe Carlos could give like a or Maria Jose could give a sneak peek on that. But I think next week, when we're talking about specifically the participatory design and the clinical evaluation of CASTOR will become more obvious, sort of.
Okay.
Maybe there's something in the direction, so we could maybe tease for next week people. So if they're interested in seeing what type of topics are evaluated. Carlos, do you have anything we could mention, not giving away next week's talk?
Yes, of course. I also I missed a point from Ray also that he mentioned about the Asian population, and we think it can be also applied to other population, and we also should go to the paper that we present the methodology of participatory science. So the interesting point with any population will be design the outfit of the robot according the expectation of the users and the clinicians and also the family involved. And this is one of the interesting part of the project, and all of details of this participatory design. It's very interesting how to extract this expectation from the users in that case, and when the parents want really like a miracles to improve the performance of the children, and how you can extract the things that you can really do with the robot and the design, and all of this will be presented in the next week. I think this is most of the most important part of the robot itself. But in the studies, we continued with the research of the joint attention, because it's a really interesting point in the research part, the assessment of the joint attention. So I showed some examples that we use it on a robot in that case. So this kind of interaction is more to point to an object and look at the child and look at the time to look at the object and the focus of attention, and also look at if when the robot asks to the child, the robot follow the object or not, and with the child. And of course, the literature have shown that the children with autism tend to follow more the instruction for the robot than the humans, and for the reason is the curiosity to understand more what the robot can do more, and how this performance of the children is going through the different sessions in the long-term evaluation. So this is one of the part. And also it's used for assessment, also to detect in very early age the possibility to have this condition. Because also in our countries, in Latin America, there is also a lot of issues in the assessment. So there are many patients with a lot of with high age that they don't know that actually have autism. So our evaluation is very complex. So we would like also to develop possibilities for the healthcare system to assess the autism. And the next part is the therapy. And in the therapy, maybe Maria Jose can say better, but we started with, as the robot is capable to interact physically, we started with therapy of proprioception. Maybe Maria Jose can explain a bit, but of course, not a lot, because we expect more attendees in the next seminar.
Thank you, Carlos.
Hi, everyone. Well, basically, in the next seminar, we are going to talk the clinical evaluation of CASTOR, but specifically two tasks that we did in terms of recognition, emotion, and physical interaction. So in regarding the physical interaction that I thought that is your interest, well, basically, we divided two groups where the child's allowed to touch the robot and the person cannot touch the robot. So we want to show you the difference between them and the behavior of the child that they can touch or not touch the robot, and what happened with that, and what is the most common behavior, what is the most common interaction, and how the spontaneous behavior happens. And that is so interesting. So I hope that the next week I can show more details about that.
Okay, I will wait next week then.
Like I already said in the beginning, the video will also go live, so you can rewatch it. Maybe specifically to Mario's question, if you go to the presentation when Diego is talking about the design and the physical properties of the body, you can sort of see which elements of the robots are meant for interaction. That might give you some ideas and we can pick up the discussion later on that. Are there any other questions? Is there anything else regarding the CASTOR project, specifically maybe about using it for other cases, or further questions? If not, I'll still wait a bit before I break up, but on the 18th of December from 2 to 3:30, we have the second follow-up session, which is talking about the participatory design. And that will be done by Professor Marcela Morena and Maria Jose, who's here today. And they will talk more about sort of the actual usage of CASTOR. Are there any further questions? If not, there's always a way of picking up. So, oh, sorry, the video just went on again. If there are no other questions, you can always contact us either through the website. So do look out for other seminars from the CRNS. There will be one next week, or there will be actually two next week. The second one is, so the last one for this foreseeable year is the one from about CASTOR. The one before is about human AI training on the 15th. So do look at our blog, see where it's at. We will link the video there as well, so you can rewatch. And feel free to get in contact either to Marios, me, or even Carlos directly, and if you want to collaborate and want to know more. Some final questions maybe, or I'm wishing all of you sort of a nice Friday.
Thank you very much, Sven. Thank you. And thank you also to all the speakers for this great presentation. And thank you, Carlos, and thank you, Diego. Also from my side.
Thank you, guys.
Bye.
Thank you.
Thank you.
Have a good weekend.
Thank you. Bye-bye.
You have a
Bye.
weekend. Bye.